Last week I finished the lesson describing how we can measure the distance between satellite and receiver using the code. The code that are the binary pseudo-random sequence that modules the carry of the GPS signal. Now we are going to see how we can measure this distance using the phase measurement. And this type of measure is a more precise than the code measure. So it's the type of measures that we do for geophysical application. So after the Rasan plot, I suppose that you know we have electromagnetic wave, electromagnetic signal, and it can be represented, we have already seen, by a sinusoidal function. So it's a periodical function. And I suppose that you know what is a phase, but I'm going to show you in a plot after. So okay, it's better to see from this picture. When the receiver captures the signal from the satellite at time t0, it measures a fractional part of the phase of the signal. Okay. I remember the light is okay, more or less. I don't remember the combination.
Yes.
It's okay. Okay. Do you check in the video?
Yes.
Okay, the last video. Okay. Do you know what is a phase in a carrier? I'm going to show you. I suppose it's better. I don't remember if I put a picture, but okay. So now I have to switch on the light for the blackboard.
Yes, you can leave it like this.
No problem. Okay. Okay. When you have a periodic signal, like this one. Okay. It means that it's like you are going around a circle. When you have finished this round, you have done a period. This the length is a wavelength of the signal. So this angle field is called phase. It can also be represented in this type of representation. So when we speak about phase, we are speaking about this angle, that means these values in the periodic signal. There is a correspondence. So when we finish to do all this run, we are here. Okay. So what we measure is a phase, is an angle. And with the instrument, we can just measure a fractional phase. It means this part. If we go around the circle, we can measure just this one. Okay, we receive from the satellite the signal. We know these initial values of the phase, and after we can start to count the integer number of cycle. So at a given time, we have just a fractional part of the phase. It means just one part. But we know that the signal arrives from the satellite. So the distance between satellite and receiver has been covered by an integer number of cycles. We don't know how many times we have run around this circle. The wavelength of a signal is like our rule. We don't know how many times we have reported this rule up to T0. When we receive the signal and we do the measure. So at time T0 we can do this measure, this fractional part, but we don't know the integer number of cycles between the satellite and the receiver. But after the satellite is moving with respect to the Earth, to the receiver, we can start to count the integer number of cycles. So at T0 we measure a fractional phase. After we can start to count the number of cycles. So at time T we know the fractional part. We know we have measured as a fractional part at time T0. We started at time T0 to count the integer number of cycles and to have the total distance between satellite and receiver. We have also to know this part, that we are going to see what is this part. And all this quantity is multiplied for the wavelength. So the wavelength for the phase give us the distance. We have seen the wavelength is like our rule. So I just count how many rules I've reported. So we have a signal with a wave length of more or less 20 centimeters. So we are going to count how many times we have to report this 20 centimeters. Okay. This is more or less what I say in this synthesis. When a receiver is switched on at time T0, a fractional part of the phase of the carry phi is measured. The fractional is given by the difference between the transmitted carry and the replica generated by the receiver. Like as we have seen with the code measure, the receiver produces a similar signal. And at the moment at T0, the receiver starts the count of the integer cycle of the phase. The number of cycles increases when the phase changes from the differences is 2 pi. Okay. Okay. This count is to take into account of the relative motion between receiver and satellite. So what we measure is the fractional part plus the integer part, and the fractional part is due to the differences between the satellite signal and the replica produced by the receiver. But the total phase between satellite and receiver is given by this measured part plus this number of integer cycle between satellite and receiver. And this quantity is called phase ambiguity phase, or just ambiguity. And it's an unknown quantity. So this is the reason because we can use code measure, code observation for real-time positioning. In real-time positioning, we have seen that we have 4 unknown at a given epoch. X, Y, Z of X, Y, Z of the geocentric coordinate of the receiver plus the clock offset, the error due to the synchronization between satellite and receiver. So we have 4 unknown, and we need at least 4 satellites. So we have a system of 4 observation with 4 unknown. So we can solve this problem. Of course, if the receiver have observation from a bigger number of satellites, we can use the least square estimation method to estimate these 4 parameters. If we want to do the same with the phase, we can see that we have another unknown. Is this integer number of cycle? We have the 3 coordinates for the position of the receiver. We have the synchronization error, but we also have this quantity. And okay, just after I come back to this. Okay. So we can write the distance, the range between satellite and receiver, like given by the wavelength multiply the total phase. And in this equation we have this quantity as unknown that are in this term. We have the synchronization error, this one, and also this ambiguity. Sorry, we have this. These are the observation, these are the error, the distance with the unknown, geometric unknown, the synchronization error, and the ambiguity. This term means that we have other errors that we are going to see. So, if we have 4 satellites, the number of unknown are x, y, z, 3. The synchronization error between receiver and satellite if we suppose that the satellites are synchronized each other, so 4 unknown. But the number of ambiguity, we have an unknown, an ambiguity for each satellite. We have an ambiguity for satellite 1, for satellite 2, 3, and 4. So increases the number of satellites doesn't allow us to solve the problem, because for each satellite we have to introduce another unknown, the number of cycles. So the solution with the phase is not to improve the number of satellites. So we cannot say, okay, so we need at least 5 satellites to have our position in real time. But we can solve the problem because this unknown number of cycles is a constant value over time. So we need more observation in the time, not just the observation at T0, but observation and T0, T1, T3, and T4, and so on. So we have a system of equation, and this system of equation at different time, the unknown, the ambiguity number for each satellite is a constant number. So we can solve the problem. Okay, in this case. In this case, we have the number of unknown are 3, 4 for the offset, 5, 6, 7, 8. We have 8 unknown. So we have to write a system with at least 8 equations, observation equations. And we can do this just with 4 satellites using observation at time T0 and time T1. Okay, so we have to increase the time of observation to use this type of, to use a phase to give us our positioning.
Excuse me.
Yes, sir.
I'm not seeing where the 8 and unknown.
8 unknown, yes. These unknown are I'm going to write X, Y, Z, the coordinate of the receiver, the synchronization error between receiver and satellite, and N1, N2, N3. No, okay. I'm going to write a more precise notation. 1, 2, 3, 4, 5, 6, 7, 8. And is it when you write your equation? Okay. You can write R1 is given by the notations that I use to confuse. Okay. Okay, I put lambda here. The distance in satellite receiver, satellite number 1, plus the ambiguity in between receiver and satellite 1 at time t0, più minus, okay. Synchronization error between receiver and satellite. Okay. This for satellite 1, sorry, I forgot the time. At time t0. Okay. Poi at time we have to do the same for each satellite. It's a long because time t0 for instance at one epoch. For the same satellite and for the same receiver, time t, we have the receiver. It depends of the time, of course, but. This for satellite equal to 1. The same for satellite 2, 3, and 4, for instance. So the important thing that this is a constant over the time. The distance changes, but it's given by the position of the satellite. We know the position of the satellite. You have seen that the position of the satellite are in the D message. So we have different distances, but we can take into account this for the satellite, the ephemerity of the satellite. So this is a constant over time. This is a constant, and here we have inside we have the coordinate. Okay. So we have a system at least at 8 observations, at least, of course. If we improve the number of echo, the number of equation related to different time, you have more observation to compute, for instance, these values using the square adjustment.
Question?
Yes, sir.
The synchronization time
Is
it the same for all the 4 satellites?
Yes, no, to be honest, it's not the same.
Oh.
But usually we can, for a normal application, we can consider the satellite synchronize each other. So we have just to take into account for the offset between receiver and satellite. But we are going to see that for the physical application, we are going to correct each satellite clock. We have a synchronization correction for each satellite. but this for very high precise application. For just positioning and navigation, we can consider the satellite synchronize each other.
Means if we decrease the number of satellites, the unknowns also decrease?
Yes, yes, of course, yes. In these cases, yes.
If I take like 3 satellites, it means NR4 will go.
Yes,
and
yes.
then
You have to. It's a very easy for a deterministic determination of the positioning. It's important that you have at least a number of observations equal to the number of parameters. Okay. Usually we want to have a redundant number of observations, more observations than parameter. In this case, we can use a statistical estimation method, like least square, for instance, Kalman filter, and so on. So we are going to see that in our observation we have more than this unknown due to other effects that are present in the GPX signal observation. Just to say, okay, I want that it's clear that with the code observation, is the observation that we use with our smartphone or our navigation system and so on. When we want to use GPS or GNSS for geophysical application, we use phase measurement. So we have to take into account for the problem of the unknown parameter, for the ambiguity. Okay, this was just an example to give you more idea about this concept of ambiguity. Okay, it was an example using a watch. If you have a watch without an arrow, you can indicate just a minute but not the hour in your watch. And I'm in this room, I say, okay, are 20 to 3, and I go out. And after this arrow is broken and it was removed. When I came back, I don't know how many times I stay outside. But when I come back in the room, I can start to count again the time, counting the integer number of cycles. But I don't have any information about the time when we broke this arrow. Okay, it's more or less a same example, if to say. So the distance between satellite and receiver is given by the number of cycles multiplied the wavelength. No, sorry, the distance in general is given by the phase multiplied the total phase multiplies the wavelength. At the beginning, we don't know how long, how many cycles we had in this period, up to T0. We can start to count after the number of cycles. So this is our unknown, the ambiguity. Okay. Okay, we have all these unknown parameters, so we have to increase. Okay, just a definition of absolute position is mean one receiver alone, not connected with other instrument. Because now for topographic survey we can use phase for real-time application of navigation, but it's a different techniques that we need, not just the satellite and our receiver, but also using other receiver around us. It's a different techniques that is used for topographic surveying application to improve the quality of the positioning, but it's not a problem now. Okay, so we have seen that this ambiguity is a constant values over time. It's not, sometimes we lose the signal from the satellite. So in this case, we have a psychosleep. It means that this, the ambiguity value at time high is not equal to the ambiguity values at time t high plus 1. Just because, for instance, as a satellite go behind a tree, behind a building, and so on. So the receiver loses the track of that satellite. Okay, so it depends how many times we have this interruption of the signal. Sometimes it's a short interaction due, for instance, I'm walking around the antenna, GPS antenna, I do some interference with the signal. This is very short. So the software that processes GPS data can repair this gap in our data. Other times this gap is too big. So we cannot repair with some specific algorithm this gap of data. So we have to introduce another ambiguity. We start again to the count of the number, integer number of cycle. So we have to introduce another ambiguity. And so we have to increase the number of unknown parameters. What about the precision? We have seen that there is this empirical rule that says that the precision is given more or less by 1 to 100, percent of the wavelength. So the wavelength of the GPS is more or less 20 centimeters. So the theoretical precision is 24 millimeters. This is just a theoretical precision. We are going to see now that we have to take into account for a lot of distortion of the signal, a lot of source of errors. Okay, but just for this empirical rule, we see that the measure with the phase measurements of the distance between satellite and receiver are more precise with the phase. Okay, this is okay. We can see now. I like this video. Okay. We are speaking about electromagnetic wave, and we have satellite very far from the Earth. So we have to take into account also for the relativistic effect in our, according to the Einstein relativistic theory, in our signal. So we are going to see this, try to see this. Okay. This one. Okay. Just a moment. Try to use it. Just a moment. Screen. I hope you can listen. It's quite good, but we can try. Otherwise, you can watch the video and again at home. Can find the link in the slide. Okay, where is it? Okay, this is one.
navigational tool used by millions of people every day. With it, drivers know where they're going. Pilots fly planes more safely. It helps construction workers build straighter roads. Farmers plant fields more efficiently. Because of it, golfers choose better clubs. Skiers find faster ways down mountains. The uses for this innovative tool are virtually unlimited. It's called the Global Positioning System, better known as GPS. So, exactly how does this incredible tool work?
So imagine you're on a field and you wanted to triangulate where you were because you know the positions of things in the distance that you can see. By measuring the direction to one object and another object, you can figure out where you have to be in the field. Well, GPS is like that, but it's larger. It's in all three dimensions, not only where in the field, but how high. And also, it's measuring time. You have 4 satellites. They're sending you signals. And you're measuring accurately where the satellite appears to be and when the signals were sent. And from that, you can figure out where you are on the Earth's surface.
Sorry. This is a geometric way to see, okay, what we have seen using equation and parameters. For me, easier using mathematical definition, but you can see the same uses this type of representation. We need a 3D position with also the problem on the satellite. We need a 3D positioning, so we have to combine this. It means that if I say, okay, I'm far from you, just 2 meters, you don't know in which direction you are. So I have to give, I'm far from you 2 meters and from him 4 meters. So we can draw a circle, another circle, and probably these circles cross each other into points. So we have to define another point and so on. In this case, we have to add another condition due to the error. Okay, it's another way to say. People often prefer this way, but I think that most of you are physics, so for me it's easier with equation. Number unknown, number of observation. Okay, but it is the same concept. Just a moment. Sorry.
From that, you can figure out where you are on the Earth's surface.
The Global Positioning System is a network of over 30 satellites orbiting 20,000 kilometers above us. They move at a speed of 14,000 kilometers per hour. Each satellite follows one of 6 orbits, arranged so at least 4 satellites are visible from any point on Earth. The satellites constantly transmit signals, easily picked up by anyone with a GPS receiver. Each signal contains information on where the satellite is and what time the signal was sent. Using this information, the receiver calculates its distance from the satellite. This is done by multiplying the signal speed, the speed of light, by the time the signal traveled. The receiver then repeats this procedure for 3 more satellites, narrowing down its location to within a few meters. To achieve this incredible accuracy, the timing information from the satellites must be extremely precise. So inside each GPS satellite is an atomic clock, the most accurate timing device ever created. The GPS is so precise, it must take into account a number of subtle effects. Some of these are predicted by Einstein's theory of relativity, an idea that revolutionized our understanding of the universe. This theory includes special relativity and general relativity. Special relativity is a theory of space, time, and motion. Key to it is the fact that motion alters time. We see time running slower for a clock that's moving relative to us. Satellite-based GPS clocks are moving past us at 14,000 kilometers per hour. Because of special relativity, they gradually fall behind clocks in Earth-based receivers at a rate of 7 microseconds per day. After Einstein formulated the theory of special relativity, he went further ahead and he proposed his theory of general relativity, which is not only a theory of space-time, but it's a gravitational theory. Key to Einstein's theory of general relativity is the fact that gravity alters time. Clocks farther away from Earth, where gravity is weaker, run faster than clocks closer to Earth, where gravity is stronger. The GPS satellites are located 20,000 kilometers above Earth, where gravity is much weaker than on the surface. Due to general relativity, satellite clocks run 45 microseconds faster daily. When we combine the effects of special and general relativity, satellite clocks run 38 microseconds faster every day. This may not seem like much, but if uncorrected, all GPS measurements would be off by 11 kilometers daily.
The effects of relativity on Earth are normally 1 part in 10 billion, and so that's an incredibly small effect, and you're used to thinking you can forget it for most things. But when you're relying on how far light travels in a particular amount of time, if you're wrong by even microseconds, then the distances that you're getting wrong are that much larger.
To correct this error, engineers adjusted the atomic clocks inside the satellites so on Earth they ran slow by 38 microseconds per day. This compensated for the effects of relativity and meant that once in orbit, the clocks ran accurately, giving us the powerful tool we have today. So, as you see, what began as an abstract theory over 100 years ago is now used in everyday technology. Every time you use GPS, you're using relativity. Whether you're heading out to meet friends, trying to find the nearest movie theater, or looking for a restaurant in another country, you'll always know where to go using GPS. So relativity is not just something to study in school. It actually affects daily events in people's lives. Your life.
It's very amazing that after they were developed, they became such an important factor in designing GPSs and navigation systems. And basically, we wouldn't have been able to do them if we didn't know much about relativity.
On the one hand, you might think of Einstein's theory of general relativity, this theory that space and time are warped, you live in a four-dimensional space-time, you might think that that's the part of physics that's furthest away from day-to-day life, and yet it should.
Okay. It's a video made from theoretical physics, so they push on the relativity theory. But it's important, I think it's nice this video because we have seen most of the things that we have introduced about the GPS, the constellation of the satellite, for 6 orbital plane, the velocity we have seen. We didn't speak about the velocity of the satellite, but I told you that one satellite goes through your head over your head twice a day, so it's quite fast. The satellites are very far. So, and the base of the measure is based on the measure is based on the clock, the atomic clock. So it's important. We have seen take into account for the relative, special and general relative theory. So I think it's a nice, yes.
I still don't hear how the general relativity is incorporated. Why it makes, because I am clear with the special relativity.
The special relativity, okay, the general relativity, they told is related to the masses. So if you have close to the Earth, if your close is close to the Earth, so the clock go slowly than when you have your close very far from the Earth. Because the Earth is a big masses with respect to the satellite. So, okay. And for this reason, it's related to the masses. So very far from the Earth is go faster. It's like
Yeah.
No, okay, you understand. Yes, inspect. No, I started to say an example, but it was for the special relativity, not for the general. Sorry. And so, in the GPS, we have to take into account for. Do you have another question? Oh, you want to explain this? Probably you know better than me the general theory of the relativity. Okay. So. Okay, you can watch the video, of course, at home. So I think this is a nice video that I found in the website. Okay, sorry, it's terrible.
Goes up in this fundamental way in GPS technology, which is crucial to everyone's day-to-day life at this point.
Theoretical physics, closer than you think.
Sorry, I use every time the laptop in the opposite side. Oh. It's the mouse button I was using. Okay. So now, okay, this is the end of this first part on GPS. We have seen the system, we have seen the signal, how we can measure the distance between satellite and receiver. That is at the base of our positioning, because we can write the equation of the distance between satellite and receiver, introducing the coordinates. So now we are going to see the error. Okay, at the moment we have taken into account just one error, the synchronization error. We are going to see a very long list of perturbations that we can have. At the end, it seems like a miracle that we can have a millimetric positioning when you see all the list of possible errors. So. It's a good homework. You can also see. Okay, there are in this lesson, the next lesson, there are 2-3 videos. That this is a general video, but there are other videos made by the geodetic community to explain some error. I think that is quite nice, and I'm going to propose you. Okay. Yes. Okay. Era già pronto. Error. Okay, I'm going to put, of course, the video in Google Drive at the end of the lesson. Sorry, last week I spent some time before put the video because on Wednesday I was out of my office and I don't have time to put this. But this evening I'm going to put the video. Okay. Okay, I think that